All right, today we're talking about double displacement reactions and solubility, and it's going to be an important topic for us, but it's also going to have a big tool that we're going to use called a solubility table. But first, we need to get through some background information so we understand some of the bits and pieces that are going to be a part of this. Number one, that if you have an ionic solid, an ionic compound that is a pure substance, it is going to be a solid at room temperature, and that's true for all ionic compounds. They are typically soluble in water, but some of them will have low solubility. And if they have low solubility, then they will have typically low solubility whether or not they are in, you've added them to water, so you take it off the shelf and you add it to water and stir it up, or they are produced in some sort of reaction. So if you're looking at compounds that are soluble or not soluble, those solubility rules are going to apply in whatever origin you have those compounds. So what we need to do is figure out some of those solubility rules and patterns, and that's going to be the job for today. So if you take a double displacement reactions, we know how to recognize them, we know how to predict the products, we know that the first thing written, the first element as a reactant will be the first element as a product as well. And we also know that the charge on the thing will not change. Charge on the positive part of it will not change. The charge in the negative part of it will not change as well. So if you were to look at a double displacement reaction like the one I have here, iron is an iron plus 3 ion as a reactant. It's an iron plus 3 ion as a product. And the copper ion is a plus 2 ion as a reactant and a plus 2 ion as a product. And that's going to be important when we are predicting products, more importantly than what we're doing right now. If you happen to have your textbook, the solubility table is on page 137, although it's in a couple of other spots as well. And bits and pieces of it are going to look like this. I've not included the entire table here, but across the top it organizes the table according to the anions. And the anions are the negative bonding partners, the negative ions. And then you have the cations, the positive ions, and they're going to be subdivided into ions that have a high solubility and ions that have a low solubility, and that's going to be the table that describes our solubility patterns. Now again, I haven't included the entire table here, and we could have more anions and we could probably find more cations, but generally speaking what we're seeing is here. Now you'll notice that in some cases most of the ions, most of the combinations have a high solubility, or most of the ions combinations have a low solubility. It kind of depends from one to the other. General patterns are kind of worthwhile knowing, but if you need the specifics of the table, you will always be given the table. But there are a couple things up there where just the general pattern is kind of helpful. Knowing that most chlorides, for example, are soluble, knowing that most hydroxides are not soluble. You'll notice that where it says for the hydroxides in particular, they're actually in a couple of the other ones as well, the OH minus, and further a couple columns down where it says group 1. You may come across a solubility table that says alkali metals. That's also group 1. Okay, so we need to know how to use this thing. So you're given a compound, it's an ionic compound, and you want to first identify the negative bonding partner, because that's how the table is organized. So here we've got Cl. It doesn't matter if it's a Cl3 or a Cl2, because that depends on the charge of the positive ion that it's with. So we're looking for chloride 1 minus on the table. We find it there in our column, and then from there we're looking into the column to find where iron is. We don't see iron listed on the bottom, so iron must be part of the group that says most. That is in the section that is labeled high solubility. That's how we use the table. So we would then predict that iron 3 chloride has high solubility, which means it dissolves quite well. On the other hand, if I were looking at, say, this one here, CuOH taken twice, we probably don't have the nomenclature for it yet, but we're looking for the OH, and we find that in the table. And then we're looking for copper. Now it's important to know that OH here has a 1 minus charge. There were 2 of them before. That means that we're looking for a copper plus 2. We don't find it in the first, so it must be in the bottom column, bottom box, which means it has low solubility. And low solubility means it does not dissolve well at all. It dissolves quite poorly. If you were to put it into water and give it a stir, you would look at it and say, it didn't dissolve. This one, it doesn't matter how complicated it gets, we're looking at the negative bonding partner first. We find that in the table, and then I want you to tell me the solubility of that one. We find SO4 in the table, and then we find where Fe, iron, belongs with that. Okay, you should be able to do that. Okay, that would end up being a high solubility. Okay, if you don't agree, we need to talk about that in class, first chance we get. Now, so far we haven't talked about reactions yet, so back to it. For double displacement reactions, what we're going to have is we're going to start by predicting the products. Now, truth of the matter is we don't necessarily have to predict the complete products when we're doing, for predicting the products of double displacement, we absolutely do. But when we're trying to figure out solubility, all we need to know is what the combinations are. Anyhow, predict the products, and then we'll look at the solubility. Now, we know how double displacement reaction works. The two metals are going to trade places, and we end up with iron now with OH and sodium, Na, now with NO3. Now we're going to find each one within the table. So I'm going to be looking for the iron and OH combination. I'm going to be looking for the sodium and NO3 combination. First one I'm going to look for is the OH. So I'll find the OH. I find iron. It's not listed specifically, so it must be part of the most, and it says low solubility. The other one, fortunately, says all have high solubility, which means, that's a good pattern to know, all have high solubility, which means that in that combination, one dissolves well, the sodium one, and one dissolves very poorly, the one with iron. So I would predict that. Now, what does that mean? Well, that means that I'm going to have something called a precipitate. The iron compound will not dissolve well, so it will be a solid. All ionic compounds are solid at room temperature, and if they're not dissolved, they will be a solid. Simple as that. Well, what does that mean? What am I actually going to observe if I'm looking at it? Well, I mentioned the word precipitate, and a precipitate is a solid product, and it's always going to be a product. I'm never going to have to worry about a precipitate on the reactant side, only ever going to be on the product side. And then because one thing in that mixture doesn't dissolve well, the entire mixture goes cloudy. Okay? And that's really important to know that if one thing out of a bunch has low solubility, then that clouds the entire thing. So if you look at this picture, you'll notice that in where the solutions have not mixed, I've got a clear colorless solution on the bottom, the solution coming out of the graduated cylinder on the top, that's clear and colorless. But where they mix, where they interact, the entire thing is now cloudy. And that will cloud the entire beaker full. So once both those solutions are mixed, one of those products is not soluble. Okay, I want you to do the same kind of thing with these. With those reactions, if you don't have the solubility table handy, you could roll back a little bit and find it, and or you can use this one here, who knew, and to come up with those. Okay, pause it, figure those out, and we'll come back to that in a second. Okay. Finally, it was a short one. It was a quick one, but using this solubility table is going to be an important skill to have. And as I said before, if you need it for a test or an exam, it will be given to you. But there are certain patterns and certain, let's call them educated guesses, you can make without the table telling you everything you need to know. We'll talk to you in class.